Let's draw the shear force and bending moment diagram for this simply supported beam under a uniformly distributed load. Now we can apply vertical equilibrium of forces to find the reactions. We'll recognize that the resultant force acts in the middle by symmetry, and that's equal to WL, and therefore the reactions are WL on 2 by symmetry. And now we can take a free body of the section that's at some distance x from the support, thereby exposing the shear force and bending moment. And taking this section anywhere along the beam gives the same forces acting on it. So if we take a vertical equilibrium of forces on that section, with upwards being positive, then we have WL on 2 minus W by the distance x minus the shear force is equal to 0. So therefore the shear force is WL on 2 minus WX. Now taking an equilibrium of moments about the rightmost point of the section, with anti-clockwise being positive, we have minus WL on 2 by the moment arm, which is a clockwise moment, and then plus WX, which is the resultant of the uniformly distributed load acting in the middle of that cut section, and by the moment arm, which is X on 2. And plus M is equal to 0. So therefore the equation for the bending moment is WL on 2 by X minus WX squared on 2. And now we can draw the shear force diagram. So we have a jump in the shear force at X equals 0, which is equal to that reaction. And at X equals L on 2, the shear force is 0, and we can see that the shear force is linear along that beam. So at X equals L, the shear force is minus WL on 2, which is again equal to the magnitude of the reaction at the other end. And now we can draw the bending moment diagram. And we know that at a pin and a roller, the bending moment is 0. So if you substitute X equals 0 and X equals L, that's what you'll get. And remember this equation that states that the derivative of the bending moment is equal to the shear force. So therefore if we set the shear force to 0, we obtain WL on 2 minus WX, and therefore X equals L on 2. And therefore the bending moment is a maximum So if we substitute X equals L on 2 for the bending moment, we obtain M of L on 2 is equal to WL on 2 by L on 2, which is WL squared on 4, minus WL squared on 8. And therefore, the maximum bending moment is WL squared on 8 and occurs at midspan. And because of the x squared term, the distribution of the bending moment is parabolic. So it looks something like this. With a maximum of WL squared on 8. Please subscribe, like and comment to help me reach more students.